All right, let's just get right into it. Large language models, LLMs, they feel like a complete superpower, right? Especially when you're working in really complex fields like network simulation. I mean, they promise to write the code for you, crunch the numbers, and just hand you this amazing breakthrough. But what if that amazing shortcut is actually leading you right off a cliff? Today, we're talking about a silent threat that could be hiding in your AI-assisted research, and you might not even know it's there.
So picture this. You've been banging your head against the wall with a complex Wi-Fi simulation, maybe in a tool called NS3. You turn to an LLM for help, and boom, it spits out code that compiles on the very first try. And the results? Well, they look just like this graph. A perfect 100% packet delivery ratio, even from 5 kilometers away. It's the dream result you'd want to publish. But this beautiful, perfect result, it's what the source material calls a siren song, and it's pulling researchers toward a really dangerous problem.
And this problem actually has a name. It's a whole new kind of error, something totally specific to AI-generated code. They're calling it LLM Ware.
So what in the world is LLM Ware?
Well, think of it like this. It's code that compiles perfectly, it runs without crashing, and it even gives you a result. But, and here's the real kicker, it's completely detached from the reality of network physics. It's not just a bug, because a bug would probably crash. And it's not just a hallucination, because the code actually looks plausible. And that's exactly what makes it so sneaky. It looks like success, but it's really just delivering scientifically useless data.
Okay, so to understand how to fight this thing, we've got to understand how it works. So let's put on our lab coats and dissect this problem. The research actually points to 3 very distinct ways LLMware shows up, which they call strains.
Here's a quick look at the 3 culprits. We've got the version Frankenstein, which plays fast and loose with software versions. Then there's the procedural trap, which completely breaks the physics of the simulation. And finally, phantom TypeIds, where the AI just straight up invents code that doesn't exist. Let's take a closer look at each one.
First on the list is the version Frankenstein. See, a simulator like NS3 has been around for over a decade, and its code has changed a lot. The LLM, well, it's been trained on all of that history, so it acts like a mad scientist. It grabs a piece of code from, say, version 3.25 and stitches it together with a piece from version 3.41, creating this monster. Now, the code might still compile, but you're now running a totally invalid simulation with parts that don't belong together. Your research becomes, as the source puts it, legacy poison. Now, the second strain, the procedural trap, is really insidious. NS3 is what's called a discrete event simulator. In simple terms, that means time doesn't just flow, you have to explicitly schedule an event to make time move forward. But in LLM, it often just writes a standard programming loop. And the result of that? Well, all the actions happen in 0 simulation time. Packets travel instantly. Things move across the map in 0 milliseconds. You've basically created a teleportation bug, and you're generating data that is physically impossible.
And this third one is my favorite, phantom TypeIds. You've probably heard LLMs called stochastic parrots. They're just predicting the next most likely word. Well, in coding, this means they sometimes predict a logical-sounding function that simply doesn't exist. Something like IPv4.enable global turbo routing. Now, a lot of the time this will cause an error, which is great, that's a safe failure. But sometimes the AI will also generate more phantom code to support its own invention, and you end up in this rabbit hole that makes it impossible for anyone else to ever replicate your research.
Okay, so now we know what the enemy looks like. But here's the most counterintuitive, craziest part of this whole thing. The moment of greatest danger isn't when your code is failing, it's the moment you think you've actually succeeded.
Every single person who's ever written code knows this feeling. That rush of pure relief and excitement when you hit that compile button and you see success. 0 errors. It works. You're thinking, yes, I'm ready to collect my data, I'm ready to write my paper.
But in the world of NS3 and LLMware, that feeling is a trap. A successful compilation is not, I repeat, not a sign of correctness. As the source says, it is a license to produce wrong numbers. This is because of something they call the optimism artifact. The LLM tends to oversimplify things. It forgets to model messy real-world stuff like signal noise or physical barriers or packet errors. So in essence, it accidentally turns off reality, which gives you those perfectly optimistic but totally worthless results. So if we can't trust a clean build, what are we supposed to do? We have to completely change our mindset. The prescription here is to stop thinking of yourself as just a coder and start acting like a forensic auditor. Your job is no longer to write code faster. Your job is to verify that the logic is actually sound.
And to help you do that, the source material gives us this brilliant, really practical checklist. Think of this as your toolkit for hunting down LLM Ware in your own work. Let's go through it real quick.
First, check the physics and the events. Is your Wi-Fi simulation showing a 100% delivery ratio from 5 kilometers away? That is a huge red flag. You should be seeing real-world physics models like path loss in there. And for events, are you seeing while loops generating traffic? That's the teleportation bug we just talked about. You should be seeing things like simulator.schedule or dedicated application model.
Next up, check your units and your APIs. Is the transmission power just set to a number, like 40? 40 what? It needs to be explicit, set in watts, for it to be realistic. And are you seeing a mix of header files from different NS3 versions in your code? That's your version Frankenstein. You have to be super strict about sticking to one single version's documentation.
Following this checklist, it's not just about debugging your code. It's actually part of a fundamental shift in what it means to be a brilliant researcher in this new age of AI.
And this quote from the source just absolutely nails it. The brilliant researcher of the AI era isn't the one who can write the most code. It's the one who can verify the most logic. I mean, think about that. Brilliance is no longer about how fast you can generate code. The AI has that covered. Brilliance is now about the rigor of your verification. It's about your ability to question, to audit, and to make sure your results are actually grounded in reality.
The source gives a perfect metaphor for this new role. Using an LLM is like using an incredibly powerful telescope. It can show you things you've never even dreamed of seeing. But it can also show you a smudge on the lens and tell you it's a brand new galaxy. Your job as the researcher is to be the astronomer who knows how to clean that lens.
So the next time an LLM hands you what looks like a perfect result, just pause. Before you write that paper, before you claim that big breakthrough, you have to ask yourself one very critical question. Is this real, or is it just LLM ware?